Okay, so today we're going to do some kinematics review. This is, of course, intended on being a review for your final exam. So in other words, I'm going to approach this review today, assuming we've already learned this in the past. It's just going to be an overview of all the stuff that we've covered in kinematics, or at least most of it. We probably will actually end up having 2 lessons on this, but it is what it is. I haven't decided yet. Here we go. So today begins our first of many formal review days. We're going to roughly follow the order we've completed this course, starting today with kinematics. The 3 main things that we're going to cover today are graphical analysis. This is where we're looking at things like distance time graphs and velocity time graphs. We'll also look at kinematics equations in 1 dimension, so just like left and right or just up and down. And then we'll also look at kinematics equations in 2 dimensions. This is where you're launching a projectile, for instance. So in other words, it's not only moving in the X direction, it is also moving in the Y direction, up and down, right? There will be some practice time, of course, today. I have a final review booklet that I've put on our Google Classroom page. But we'll get to that when we get to that. Here we go. So first of all, what is kinematics? Hopefully you at least have some idea if this is at the end of the course, but just in case you've forgotten, kinematics basically describes how things move. So in other words, it answers questions like how far, how fast, how much time, how much acceleration, those kind of things, those actual describing features about an object that is moving. Now in physics 20, we dealt with 2 general situations. We looked at uniform motion. This is where you have a constant speed, or in other words, there's no acceleration. Your object is not speeding up, it's not slowing down. It is moving at a nice, predictable speed. For example, if you're on the highway and you're setting your cruise control, for instance, to 100 kilometers per hour, that is uniform motion more or less because you are maintaining more or less a constant speed of 100 kilometers per hour. Now these are pretty nice. You only have one formula. It's V equals D over T. Of course, that just logically would make some sense, especially if you're going, let's say, 100 kilometers an hour. Then you know after, let's say, 3 hours, if you're going 100 kilometers per hour, after 3 hours, you've gone 300 kilometers. They're pretty predictable, right? There's no speeding up, no slowing down. It's pretty clear to see where something is going. Now, the other situation we dealt with was uniformly accelerated motion. This is where you have a non-zero acceleration causing your object to speed up or slow down. But this is where that uniform word comes in, but the amount of that acceleration doesn't change. In other words, the rate at which your speed is changing is not changing in itself. It's weird to start thinking of an acceleration that changes. I think the word for that is called jerk. We don't deal with that in physics 20 at all. But in terms of uniformly accelerated motion, where you have a constant acceleration, there's many formulas for these. There's like six or so of them, I think. These are all on your formula sheet. We call them the kinematics equations. They're up in the top left-hand corner of our formula sheet, at least the one we're using at this time. So yeah, you just use them, right? You make a data bank, you say, what do I have? What am I looking for? And then you go to town, right? Anyway, we'll get to that in a bit. First of all, I want to go over graphical analysis because this is one of those weird things that we did talk about early in the course, but then it doesn't really come back too much, except for now, of course. So let's suppose we have a position time graph. In other words, we have on the y-axis position, saying how far something went, and on the x-axis, we have our time. How can we find the velocity at different points? So a velocity, of course, just to refresh your memory, it's the same idea as speed. It just has a direction. That's more or less how that changes from that. But a velocity is a change in your position over time. If you look at this graph, we can clearly see that the position of this object is changing as time goes on. And if you think about it between each section, the rate at which the position is changing over time is also changing. In other words, we are making a slight change in the first second, and then a little bit more of a significant change in the second second, and then a pretty substantial change in the third second. Then it gets steeper and steeper as time goes on. That intuitive understanding here actually tells us how to find the velocity. The velocity on a position time graph is just the slope of your graph. Now, if you're looking at it at different points, that just means you have to find the slope at different points. This is kind of a Mickey Mouse part of physics 20. There's not really a real formal way of doing this, but the basic idea is if you have some sort of a straight edge like a ruler, you can find the point that you're interested in, like let's say at time 3 seconds, and you just draw a line that grazes the surface of that point at that point right there. Now that was terrible. I don't have a ruler when I'm using this little pen tablet thing that I've got. But the general idea is just to draw a straight line and then figure out the slope from there. And in case you've forgotten how to find the slope, that's all right. It's just your rise over your run. So in other words, just figure out how much you rose up by. So in other words, you'd look here, you'd say, okay, that's about 25, and this is like maybe 12 or something like that. You just estimate on these ones, unless you actually know the points, of course. And then the run is just how far over we went. So in this case, it looks like it's somewhere between like 3.8 seconds and maybe 2.8 seconds. So you just figure out how far you ran in that situation. And again, your slope is your rise over your run. Again, pretty Mickey Mouse. When you're just finding the slope at different points, you just draw a line that grazes the surface. We call that a tangent line at whatever point you're interested in. We didn't really focus on this a huge amount in this course. It was something we just kind of threw in early on in the course, but it is still something important to know. As a side note, if any of you have taken calculus before, I know some of you in Physics 20 this year have, you would understand that, there's actually a better way of finding this. If you knew what the equation is for it, it's called taking the derivative, but that is way beyond Physics 20. I'm not even going to get into that today. So the Mickey Mouse way it is, at least for Physics 20. Anyway, moving on. Now, a different kind of graphical analysis here. This time we have a velocity time graph. This is where, of course, we have a velocity on our y-axis, and once again, the time on our x-axis. This is not to be confused with a position time graph. What this graph is showing us instead is how the object's speed, or in other words, its velocity, is changing over time. The other one showed us its position changing over time. So don't confuse the location on this graph as being a position. It's actually just telling you its speed. So what does the slope of a velocity time graph tell us? Well, slope, just like in the last question, shows you how much something is changing over time. A changing velocity over time is known as an acceleration. So the slope on a velocity time graph tells us the acceleration. So we can see in this case right here, this section 1, there's a positive slope. It's going up, right? Puff, puff, positive, if you remember slope dude. Since it has a positive slope, that tells us it has a positive acceleration. In other words, it is speeding up. That shouldn't be a big surprise. Our starting speed looked like it was somewhere around 20 meters per second, maybe a little less. And then after this slope here, we're up at 30 meters per second, right? So it's sped up. There was a positive acceleration. During this section right here, notice it looks like our slope is 0. It's just a flat line. So since that is a 0 slope, that means we have 0 acceleration. We are not speeding up and we are not slowing down, which again, shouldn't be a surprise because at the start over here, we are at about 30 meters per second. And then way over here, we're still at 30 meters per second. As for this last section right here, this is a nice negative slope, if you remember slope dude, right? Since that's a negative slope, that tells us that our object is slowing down. In other words, it is losing its velocity, and that shouldn't also be a surprise because we're going from 30 meters per second up here all the way down to 0 meters per second down here. Now, the last part of this slide here says, how can we find the displacement? In other words, how can we use this velocity time graph to figure out how far this vehicle traveled? This one's really weird. You may or may not remember this. It was probably the most bizarre thing we did with graphs. To find the displacement, you need to find the area under the curve. So in other words, if you look at your actual graph, you have to break this down and find the area underneath this curve. Now, it's not asking us to find the displacement, so I'm going to save myself and you guys the trouble of actually calculating this, but I think it is still useful for me to show you how we would break this down. You have to break it down into workable shapes. This one is a little weird. I'm actually glad I threw this one in here. Probably the most obvious shape that you can form in this is if I start right here, bring this straight down as best I can to about there, and then take this point and bring it straight down, which I think would be about to there. We notice we have either a square or a rectangle in here. And of course, the area of that is just length times width. So if you were to find the area of this section right in here, you just take the length and the width and you multiply them together. As for this one on the far right, this one over here, notice this is just one gigantic triangle. Well, a triangle is a basic shape. We just find the area of that by going base times height divided by 2. Maybe I'll even write that here. Base times height divided by 2. This section over here with section 1, this one's a little trickier. Notice this shape overall isn't exactly a simple shape. Well, we can simplify this by making it into a triangle up top here. So this would be another base times height divided by 2, just a very small one. Keep in mind the height would only be this section right here, and the base is only this section. And then we also have a rectangle, which is a much simpler shape, of course, just length times width once again. The moral of the story is, when you're asked to find displacement from a velocity time graph, you have to find the area underneath the curve. That can take a little bit of work because you have to break it down into workable shapes. Always think about how you can make this something a little easier. Don't try to like tackle it all at once. You're not going to be able to find the area under the curve using any simpler methods, at least not with what we know in Physics 20. For those of you, once again, who have calculus, you might remember, hey, we actually do have another way of doing that. Although I wouldn't say it's simpler. I wouldn't say it's simpler at all. But anyway, we won't worry about that. This is physics. This is not calculus. Anyway, so we're going to move on to kinematics equations. These are all on your formula sheet, of course. Even the one for uniform motion, like V equals d over t, even that one's on your formula sheet. Remember that the key to using these was to be able to identify 3 things you have and 1 thing that you want. If you have enough things to throw into the equation, with the exception, of course, of the thing you're looking for, you have enough to solve that equation. Really, it just comes down to 2 things. Make a data bank. I'll even write this in here. You know what? Make a data bank. That's your number 1 goal. Write down what you actually know. And then number 2, use some algebra on this. In other words, rearrange this formula to get what you're looking for. You can rearrange it before you plug the numbers in. You can rearrange after the numbers get plugged in. Honestly, that's usually what I do, but it's up to you, right? In terms of algebra, if you're really worried about how to rearrange an equation, you know, we're pretty late in Physics 20, but you can always look up some videos online. I'm sure you'll be able to find something that can help you out. Anyway, so from there, pick the kinematics equation that has the variables you have and want for one-dimensional equations. So if you're just going left and right, or if you're just going up and down, this was all there was to it. When you have 2-dimensional questions, though, like when you're launching something, so it's not only going left and right, but it's also going up and down, such as with projectiles, it was trickier. We'll get to that a little later. It's about breaking it down into X and Y components, but we'll get there when we get there. So here's our first example here. Now it's up to you whether or not you're comfortable or not. You could pause the video after I finish reading this and try it on your own, or you can just watch me go over it. It's up to you. But we have Kira, who stopped at a red light, and she notices that Mr. Scott stopped next to her. As soon as that light turned green, Kira floors it and accelerates to a velocity of 135 kilometers per hour south in 8.4 seconds. Use your knowledge of kinematics to find her acceleration while Mr. Scott calls the cops. Anyway, pause the video here, give this one a try if you want. I'll go over it in 1 second. Okay, so I'm going to go over this one now. First things first, I'm going to be honest with you. I haven't even done this question on paper beforehand, so I'm going to be throwing numbers in my calculator as we go. But first things first, I'm going to start by making a data bank. One thing I can see right off the bat is that she's accelerating to a velocity of 135 kilometers per hour south. That is her final velocity. So VF is 135 kilometers per hour south. Not a bad idea to include direction here, because remember, direction tells you, like south in this case, we'll say is positive. North, I guess, would be negative in this case. It's always a good idea when you can, right? Another thing I see, another obvious one, 8.4 seconds. Well, that, of course, is a time. So time is 8.4 seconds. One thing that isn't so obvious here, you might not have caught it right away. We actually know what her initial velocity is. Notice it says that she was stopped at a red light. That means her initial velocity, VI, is 0. You can say that's 0 kilometers per hour. You can say it's 0 meters per second. It's just 0 no matter what unit you're using. So I'm just going to call it 0. Now, the one thing we're looking for, though, is her acceleration. So what we're looking for is A. So A is our question mark here. Notice we have 3 things. We need to find the 4th thing. Now, we need to be careful here, though. When you're using the kinematics equations, it is always a good idea to use common base units. Now, I think you could throw in kilometers per hour in here. You just end up getting an acceleration that is in some weird unit. I think it'd be kilometers per hour per second or something like that. That's not the best unit to be using here, so I wouldn't recommend it. So instead, before we even begin, I'm going to turn kilometers per hour into meters per second. And remember, the easiest way to do that is just to divide by 3.6. That's the conversion factor between the two. So 135 divided by 3.6 gives me a nicer number than I expected, 37.5 meters per second. Now I feel comfortable and ready to go. Let's have a look at our kinematics equations. So what I'm doing right now is I'm looking at my formula sheet and thinking, what formula could I use to get what I want here? Well, I'm actually glad I'm doing this because it's actually one of those sneaky ones. On your formula sheet, there's one that says A equals V over T, or more correctly, it says A equals delta V over delta T. And it even calls this an average acceleration. This is kind of a weird one. Totally forgot to mention this earlier on, but I did mention this earlier in the year, of course. This delta means a change in your velocity, right? So a change in your velocity over a change in your time. Well, a change in your velocity is just the difference between your initial velocity and your final velocity. So what I do instead, even though this isn't on your formula sheet, I just recognize that this formula is actually A equals VF minus VI, so the difference between those two, or in other words, the change in your velocity, over your time. Now, delta T, a change in time, it's rare we ever use that as a change because it's usually just like, okay, yeah, it took 8.4 seconds. Your starting time was 0 seconds, so your final time, 8.4, is just your change in time, right? Anyway, throw these numbers in here. We've got A equals VF is 37.5 minus VI, which is 0, divided by T, which is 8.4. Throw that in your calculator because we have all our nice base units. It shouldn't be too big of a deal. That gives me, oh, how many sig digs do I need? Let's see. We need 2 sig digs here. So to 2 sig digs, I've got 4.5, and that's an acceleration. So it's meters per second squared, or in other words, meters per second per second. There it is. That's our acceleration. Wow, that's actually a pretty decent acceleration. That's, yeah, usually accelerations are pretty small numbers, but hey, she floored it, I guess. She ended up at a absolutely ridiculous speed. This is not me condoning this. Do not go to that speed. Call the cops. Swear. Anyway, moving on. Next question. Clayton is standing on the edge of the roof of the school. He throws a rock straight up in the air at a velocity of 14.0 meters per second up. If the school is 12.0 meters tall, how long does it take the rock to hit the ground? I suggest you pause the video here and give this one a try. All right, I'm going to go over this one now. First of all, like always, make a data bank, right? So we know what the initial velocity of the rock is. That would be VI equals 14.0 meters per second up. So it's nice, at least that was already in meters per second. And I'm going to say up is my positive direction. Now the school being 12 meters tall, we're going to assume that this rock is actually going to go all the way down to the ground, so the bottom of the school. We know Clayton is standing on the edge of the roof of the school, so we'll assume that the rock ends up on the ground, you know, at the base of the school. So what we'll say is the distance that that rock traveled is 12 meters down, or in other words, negative 12 meters up. Remember, it's really important that we have our directions always in the same way. So if we're saying up is positive, we have to make sure everything else is in reference to up. So it's negative 12 meters up. That's where that rock ended up going. Now, what we're looking for is how long it takes the rock to hit the ground. So time is the thing we're looking for here. But notice we've only got 2 pieces of information. We need 3 to figure out the 4th missing thing. Well, that 3rd thing that we actually have, despite the fact that it wasn't given to us, is our acceleration. Because this is an up and down question, we know the acceleration is just gravity, and gravity is 9.81. But we got to be careful. It's 9.81 meters per second squared down. And because we've already said up is a positive direction, I'm going to call this negative 9.81 meters per second squared up, right? Your directions always have to match, right? If you don't have matching directions, you just fix it by putting a negative in front of the one that doesn't match. That's about it, right? Now, of course, up and down go together. Left and right don't go with up and down. That's what we're going to get into a little later when we do a projectile question. But anyway, let's see what we can do to solve for this one. I'm going to glance at my formula sheet. I think I see what formula I have to use. Oh, I do, but there's something kind of funny about this one. So the formula I see to use is the one that says D equals VIT plus 1/2 AT squared. Now, the reason I say that this is kind of funny is T is our unknown. If we were to plug the numbers in here, you'd have a T here that's unknown and then a T squared here that is also unknown. Oh, I'm really glad I actually threw this one in here. This is a weird one. Moral of the story is, I'll even just show you. If I throw these numbers in here, negative 12 equals, that would be 14 times T plus 1/2 negative 9.81 T squared. If I plug that in here, it becomes like a quadratic from Math 20. Now you could solve this by just like cleaning up this, so 1/2 times this, and then even moving the 12 over by adding it over. You could solve this using the quadratic formula. There's nothing wrong with that. But I'll be honest, that's really uncomfortable to me. Like, I really don't like doing that. So whenever possible, I like to get around that if I can. So I tell you what, because this kind of gives us a bit of a stumble, like I'm just going to go like that, like what the heck. Because this gives me a little bit of a stumble, what I'm going to do is I'm going to do, this is actually probably the long way around. I'm going to find my final velocity first. Once I have my final velocity, I can use that with a different formula. That way time won't be as awkward to find. So if I'm looking for my final velocity instead, using the things that we have, I think the formula I can use is the one that says VF squared equals VI squared plus 2AD. Throw our numbers in here. We have VF squared equals 14 squared plus 2 times negative 9.81 times negative 12. Throw all that in there. Give me 1 second. 14 squared plus 2 times negative 9.81 times negative 12. This gives me 431.44, and then we have to square root that. If you square root that answer, we get VF equals 20.7711, and then a bunch of other stuff. I'll just leave it at that though. Now, that of course is in meters per second. Also, we have to use a little bit of critical thinking here. If a rock is falling down, I don't believe that we would have a positive velocity here if we're saying positive is up. So instead, I'm going to make this negative 20.7711 meters per second up, because of course, as the rock goes up, it then comes down and it has a faster speed than it was when it was launched, because of course, it's falling off the roof of the school. Anyway, now that we have this final velocity, I can now find my time by using a different equation altogether. I think the different equation that we'll want to use is the one that we actually used on that last slide. I'll just do it over here. A equals VF minus VI over T. Throw your numbers in there. We know we have negative 9.81 equals negative 20.7711 minus 14 all over time. We can clean up the numerator there. I'm really going the long way around with this one, but that is fine. Negative 9.81 equals negative 20. Give me a second, negative 20.7711 minus 14. I guess that gives us, oh yeah, of course, negative 34.7711. That should have been more obvious, I guess. But anyway, multiply by time, divide by negative 9.81. And long story short, we have T equals, how many sig digs? 3 sig digs. So T equals, I got 3.54 seconds. Holy smokes, we went the long way around with that one. So long story short, no matter how you do this, you can either just use the quadratic formula on this, which I really didn't want to. You have to realize though, when you use the quadratic formula, you get a positive answer and a negative answer. Obviously, the negative answer would be garbage here. The rock's not going to hit the ground a couple seconds before it was thrown. That doesn't make any sense. Or you could just go the long way around like I did. That way you don't have to bust out the quadratic formula. Looking at our formula sheet, I don't see the quadratic formula on there anyway. I know on your final exam, I do give you the quadratic formula if you ever want to use it. Truth be told, I don't think you do, but it's there. It's an option if you wish. I guess you could use a graphing calculator for that too. No, never mind. We'll just always do it algebraically. It is what it is. Anyway, last thing we got to cover today, I swear, projectile motion. So with projectiles, remember that it's important to break it down into an X component and a Y component. In other words, there's a left and right, and there's an up and down. It's very important to remember that for simplicity's sake, we always assume that the X component has uniform motion. In other words, the acceleration is 0 unless otherwise stated. I don't think it'll ever be otherwise stated. In the X direction, we are always assuming that your velocity in the X direction is equal to your distance in the X direction divided by your time. Now, the only common variable that completely links the X and the Y is your time, generally speaking. That's why when I wrote this formula right now, I didn't call it time X. Your X time and your Y time, generally speaking, will always be the same. Now, the initial velocity kind of links them. So this Vx is also like your Vix, your initial velocity in the X direction. The initial velocity kind of links them. It gets broken into an X component, which I always just call Vx, and a Y component, which I call VIY. So whatever initial speed, we'll just call that the true V, whatever initial speed, how about I call it the true VI actually, just to be more careful. Whatever that true initial speed is, it gets broken down into an X direction and a Y direction. And the way we do that is just using a little bit of trigonometry. So that was SOHCAHTOA stuff. All right, so if we know the angle, we can use SOHCAHTOA to figure out one of those missing pieces. Fingers crossed, at least, right? Anyway, let's do a single example. This is it, I swear, last example of the day. Maybe I shouldn't swear yet. There we go. Yeah, it is the last example of the day. See, I had to double check there. Anyway, so the example is a paintball. A paintball is shot to the right at an angle of 25.0 degrees. If it hits a target at the same height from which it was shot 3.00 seconds later, find the distance between the shooter and the target. Try this one. You'll want to draw a picture, believe me, as well as make a data bank. Try this one. I'll go over it in just a second. All right, so I'm going to go over this one. I'm going to start by drawing a picture. I'll just do it way up here in the top right corner of the page. Let's suppose this is the paintball gun, and let's say this right over here is the target. The paintball is shot at an angle of 25.0 degrees. So I'm going to do like a dotted line as my horizontal kind of thing here. It's launched at 25 degrees. This is harder to do on a tablet thing than you'd think. Anyway, the paintball flies in an arc, and then it hits the target at the same height from which it was shot. All right, so I need to make a bank. First things first, we don't really have a lot of information. We know this angle, that's about it. Well, I guess we also know the time. So here's the thing. I'll make an X component list. So I'll call this the X comp, and I'll call this the Y comp. Time is a nice thing to have because time is something that links both the X and the Y together. So I'm going to start by saying time is 3.00 seconds, but it's also 3.00 seconds over here. Now, in terms of an X velocity, we'll call that a Vx, we have no clue. I have no idea what that X velocity is. I also have no idea what the X distance is. That is what we're trying to find. We're trying to find the distance between the shooter and the target. That would be our dx. So I'm going to put like a little star here. That's what I'm hoping to find. What we can see here is since I'm looking for my dx, I need to find Vx, in other words, or I need to find Vx first in order to find that dx, because all the X components are connected and then the Y components are connected with themselves. But since we don't have Vx, we have to look at our Y component to see if we can get Vx somewhere. It doesn't look like we have a lot in the Y direction, but I promise you we actually have more than it seems. Another thing we have in the Y direction, and we pretty much will always have this, is our acceleration. The acceleration in the Y direction is, of course, just your gravity, right? So I'll say A, acceleration, is negative 9.81 meters per second squared up. I'm just going to be safe here and say that up is a positive direction. That's why I'm making that one negative. We actually have something else in our Y direction that might be a bit surprising to you. Notice it says it hit the target at the same height from which it was shot. That means during this whole motion right here, from the beginning to the end, in terms of a Y direction, up and down, the paintball ended up at the same height from which it was shot. In other words, the paintball's Y distance, so it's dy, or Y displacement, I should say, the paintball's Y displacement was 0. It didn't end up going anywhere in the Y direction. It went a long distance, I think, at least we'll find out, in the X direction, but it didn't go very far in the Y direction or any distance at all, to be honest. Now we have 3 things in our Y direction. That means we can solve for whatever missing 4th piece we want. Now, something that's going to help us link this back to our X direction is our initial velocity in our Y direction. So VIY, if we go to our picture here, VIY would be this component right here, like this opposite side of our triangle in the launch triangle that I drew here. This can be connected to our Vx, our initial X velocity. We can connect this, of course, using a little bit of trigonometry. Now, the trouble is we can't use trigonometry quite yet because we need to figure out what our VIY is, but we can use some of the kinematics equations using our Y component information to find that. Anyway, I'm rambling a lot here. So let's look at our formula sheet. Let's figure out what formula we could use. I think the formula I could use for this one is the one that says D equals VIT plus 1/2 AT squared. This time around, because time is known, we don't have that same problem that we had with the last one where we had 2 unknown T's, right? Anyway, throw our numbers in here. We have 0 equals 3 times, VT Vx, we'll call that Vi, Vx, it'll be the same thing here. Vx times 3, there we go, plus 1/2 times a, which is negative 9.81, times t squared, so 3 squared. I'm going to clean up this bit here first. So I've got 0 equals, we'll just call that 3Vx, plus this whole bit right here, bear with me, 1/2 times negative 9.81 times 3 squared. This gives me plus negative 44.145. We can move that over to the other side. So we can have positive 44.145 equals 3Vx. My writing's really messy today. You can tell I haven't done this in a while. Anyway, divide by 3 on both sides. We have Vx equals, we're going to want to keep all our decimals here because we're not done. Oh, why am I saying Vx? Geez Louise, you guys probably were even shaking your head before. That's not Vx. This is VIY. Whatever, same idea here, same idea. 3VIY, there we go. Anyway, so VIY in this case, my mistake, guys. VIY is 14.715 meters per second, and that would be up. And the reason we know it's up, of course, is because it told us, right? It's being shot to the right in an angle of this. We can assume it's being shot upwards. Otherwise, it's not going to hit that target. There's nothing to bring it back up. Anyway, what we know now is since we know VIY, we know this piece right here, we can use a little bit of trigonometry to find Vx. If I kind of expand that triangle just down here so you can see a little bit better, we know that this is 14.715. We know this is Vx, like actually Vx this time, not me being silly. And then this is 25 degrees. Notice we could say that this is our opposite side to our 25 degrees, and Vx, which is something we'd like to have so we can find dx, that would be our adjacent side. If you think back to trigonometry, SOHCAHTOA, write that out again, SOHCAHTOA. If you think back to trigonometry, if you have opposite and adjacent, that means we're going to have to use tan. So I'm going to say tan 25 equals the opposite side, which is 14.715, divided by the adjacent side, which is Vx. To solve for Vx, we just need to multiply by Vx and then divide by tan 25. Make sure your calculator is in degree mode if you haven't done so already. Anyway, 14.715 divided by tan 25. This gives me Vx equals 31.5564. Whew, believe it or not, we're not quite done yet. We still need to find dx, but the good news is we are almost there. The last thing we've got to do here is realize that in our x direction, we only have v equals d over t. We know what v is now. We know what t is. We can just solve for d. So v, of course, was 31.5564. This equals d over 3, multiplied by 3 on both sides. Bingo, bango, bongo, we have d equals to how many sig digs? 3 sig digs. We have d equals 94.7, I think is what that would be, 94.7, and that is meters. And just for some added fun here, notice it's to the right, so we'll say to the right. Whew, holy smokes, that was a lot to it. Looking back at the question again, I guess we didn't need the direction because it does say distance. Distance is what we call a scalar measure. I'm not gonna flout it though. It is what it is, right? The distance, even if you give a direction, that is totally fine. 94.7 meters though, that is correct. Anyway, that was a long video today. I apologize for that. But for practice, I'd like you guys working on the final review booklet. I did post it on Google Classroom. It's got a whole selection of questions from the whole course. If you need any help, of course, please make sure you are reaching out. You can also check the answer key that's posted on Google Classroom. Best of luck.